Okay, what's the frequency of this and how much energy does it pump out and where is it in the spectrum? So we need the speed of light, so I just use 3 times 10 to the 8th meters per second. And what we're looking for is frequency, and the units for frequency are 1 divided by seconds. So I just start with 3 times 10 to the 8th meters divided by seconds, and then I can put 5.5 times 10 to the negative 7th on the bottom down here, meters, and then the meters cancel out, and I get a number that's got 1 over seconds for its unit. So I got 3e8 divided by 5.5 e negative 7. So 5.5 times 10 to the 14th. And then the energy portion of it would be so what we need is 6.626 times 10 to the negative 34th joules times seconds. So I'm just going to start with that, 6.626 times 10 to the negative 34 joules times seconds, because I need an answer that's got joules as its unit because I'm looking for energy. I need to get, I'm going to use 3 times 10 to the 8th meters per second to cancel out the seconds. And then I'll use 5.5 times 10 to the negative 7th meters to cancel out the meters. So I've got 6.626 e negative 34 times 3e8 divided by 5.5 e negative 7. So I get 3.6 times 10 to the negative 19th joules. Okay. How was I supposed to figure out it's where it was in the electromagnetic spectrum? You could have pulled up a spectrum, or you could have remembered that it was 400 to about 750 nanometers for the visible spectrum. And then this 5.5 number, if I make this 10 to the negative 9th, this becomes 5500. And so then I can change this to nano, call it meters. And so that we're at 5,500 nanometers. So we're longer than red. So what's that? Infrared. So this is in the IR spectrum. Okay. Anybody want to question how I did that second calculation?
What where you found the energy?
Yeah.
Just took Planck's constant times.
There's nothing wrong with it. Did anybody do anything different?
I just honestly found it on one of those things that shows you like the different wavelengths and what they correspond to.
Oh, okay.
There's one that had energy on it. So.
Okay. But nobody has a problem with how I did that calculation? Somebody usually steps in and says, how come you just didn't use the frequency you calculated and multiply the frequency by the Planck's constant? We could have done that. Does anybody know why that's typically a bad idea, especially on a standardized test? When you calculate something, if there's given information and you can actually calculate the answer from the given information, do that. Never calculate an answer to a question from an answer you already calculated, because you end up having rounding errors. And when they're trying to hose you on standardized tests like the GRE, they'll move the decimal, or they'll give you a mistake. Like letter A will have the correct answer the way you calculated, but it'll be off in like the second decimal place, and letter E will have the answer with the correct number in the second decimal place. So just test taking technique. If you can calculate it from what's given in the problem, do that. Don't use the work you've already done if you can get away with not doing that. Is anybody in here for nursing? No. Usually that's all this class is. So yeah, you guys crash in the stereotype. So this is usually something that they'll do on that ProCalc test where they're trying to figure out, where you're trying to figure out how much dose you should give to somebody. And so then you end up giving somebody like 10 extra milligrams or you just killed somebody kind of thing. Okay, so I've got a photon with this amount of energy. I want to calculate a wavelength, and I want to know where it's going to be found on the spectrum. So I need wavelength, so that means I need a meters. So I'm going to start with 3 times 10 to the 8 meters per second. And then I'm going to cancel out that second by writing 4.5 times 10 to the 14th. And then second goes up top because this is inverted. So the seconds cancel, and so we end up with 3E8, 4.5, E14. Meters. And then we can also go ahead and calculate 6.626 times 10 to the negative 34th joules times seconds. And then this time we can do, let's poorly turn on. This time we put it up top, so it's 4.5 times 10 to the 14th divided by seconds. The seconds cancel. And so 6.626 E negative 34 times 4.5 E14. So I get 3 times 10 to the negative 19th joules. It's reasonable. And so then I can do the same thing with this guy and make this 6700 nanometers. Just convert that number into that. And so then it looks like, again, we're at IR. Yeah, we're probably in IR still. What do you want to do for line spectra? What drawing did you pick?
Like an atom with the electron orbitals.
Like this. And then you can have something like electron goes up to here, and then it goes back down to there. And when that comes off here, that'll give like electromagnetic radiation. And because all of the atoms' electron configurations are different, all of the atoms will generate a different spectrum. Because if this one's hydrogen, then this can't be helium because you've got 2 electrons down there, so the amount of energy needed to cause it to jump is going to be more because those electrons are closer to the nucleus. And so when it returns, it's going to give you back a different color. Does that make sense? And if I'm talking about a bigger atom like sodium, this transition can never happen because the 1s2 electrons and the 2s2 electrons and the 2p2 electrons are all off limits. The only electron doing anything is the 3s1 electron. So again, it's going to be all different transitions. All right, particle. What about a wave? Interference, and what else? Refraction and interference are the 2 reasons that it looks like the observable data presents wave when I'm looking at it in the interference refraction scope, but when I'm looking at it in photoelectric effect, it looks like a particle. All right, so the beta particle is negatively charged, so it's going to be attracted to the positive. The alpha particle is positively charged, so it's going to be attracted to the negative. This is about 8,000 times more massive. So this has less momentum, so it can more easily be turned. And this doesn't move because there's no charge. All right, how about this gas-filled radiation detector? I got a can, got a wire. The wire goes to the battery. Got a counter. And then it goes to the can. So I've got argon, usually. Radiation comes in here and smacks the argon, and I'm left with an argon with a positive charge and an electron. The center wire here is positively charged with 2,000-ish volts of electricity, and the can is negative 2,000 volts of electricity, because this is the anode side of the battery, and this is the cathode side of the battery. So the electron hits that wire, travels through the wire, travels through the battery, gets counted, and then travels back to the can, where it can make a connection back with the, I wrote silver right there, where it can make a connection back to the argon. And then this thing can turn back into just regular old argon gas, where if it gets hit with enough energy again, radiation, then it's going to do that same thing. So you can continually count those argons losing their electrons and regaining them. All right, so standing 25 meters away from a source, I'm exposed to 129 mAh gamma. If you move back 15 feet, place 4 inches of lead, what's your new exposure? Okay, so it's intensity, I'll just put X, and intensity Y, and then radiation, oh wait, distance, sorry. Distance squared Y divided by distance squared X. So I'll just throw numbers in. So we'll put, say, we'll put 120 millirem per hour here, and I've got intensity at distance Y, and so then this is going to be 25 feet squared, and this is going to be 40 feet squared. So intensity Y is equal to 120 times 25 squared divided by 40 squared. That'll be millirem per hour. $120 times 25 squared divided by 40 squared equals 40, I'll just make it 47 millirem per hour. Okay, so do the math, forget about the shielding, and then the tent thickness for gamma using lead is 2 inches. So for every 2 inches, the amount of radiation is reduced to 1/10 of what it was before, so this gets moved twice. So you end up with the shielding making this 0.47 millirem per hour would be your answer. Are we okay with that? Half-life, time needed to reduce You can either use mass or moles. Moles makes more sense, but everybody usually uses mass because it doesn't really matter. So half of the atoms are no longer that isotope once that half-life has gone by. All right, so I've got 2,048 grams of cobalt-60 with a half-life of 5.27 years. How long will it take to reach 256 grams? Okay, so 2048, and that's going to be at time equals 0, and then 1024, which is 5.27 years, and then 512, I don't know, whatever that is, 5.7, 5.27 times 2, so this is 10.54, and then 256. 15.81 years. This particular isotope of cobalt is super important because the particular gamma radiation that it generates is on the smaller end of the gamma spectrum, so it actually has more penetrating power than your average gamma. And so when you produce anything inside of when you produce any metal, cobalt cannot be a part of it. If I'm talking about a nuclear power plant, that's not an okay thing, because it's got a decently long half-life. So anybody who's walking around inside that area would be exposed to a high energy gamma. Okay, this last one here. What 3 things do you need? Okay. Mag, how about internet? What else?
Wire spinning around them.
How about a wire? And what else? Relative motion between the two. It's phrased like that because you can either move the wire through the magnetic field or you can move the magnetic field around the wire. Either one of those is totally fine. Okay.
Rob, for the half-life question up there, could you use the that one formula, like the
That would totally work as well.
over like the LN2, like the half-life of the LN2,
So you could put down 5.27 divided by the natural log of 2, negative 5.27, times natural log of 256 divided by 2048, and that had better give you 15.8 years as your answer. Okay.